It's worth pausing at this point to consider how ANDs are implemented. In all the previous videos, we've inferred that they're programs written in software. But in fact, they might be implemented as electronic circuits or optical systems or some other type of hardware. Consider, for example, an analog electronic implementation. One suitable version of this is shown on the screen. Here, the programmable amplifiers are acting to introduce weights to the inputs. The weighted inputs are then added together by the summing amplifier and squashed with a suitably saturating amplifier. Similarly, we can envisage a digital version, as shown on the screen now. The advantages of hardware implementations of ANDs are several-fold. Firstly, their speed. Circuitry is always faster than programmable computers when using the same technology. Secondly, there's parallelism. In the hardware version of a AND, signals propagate through neurons at the same time, just as they do in biology. Whereas in a serial computer, each neuron is processed sequentially. This not only feeds into the speed issue, which we've just discussed, but may be important in consciousness in very complex ANDs, as we'll discuss in later videos. Because of this, you might hear software implementations referred to as simulations of ANDs rather than pure ANDs. On the other hand, software has the advantage of flexibility. Network size and topology can be configured easily, something especially important in evolutionary ANDs, which we'll discuss later. Programmable electronics can overcome this problem, however, and FPGAs, field programmable gate arrays, which are a type of programmable logic, are often used to implement them. There are many other possible interesting implementations. In fact, as early as the early 20th century, a mechanical implementation was suggested, and more recently attention has focused on optical systems and those involving quantum mechanical devices.